David Smith here with another Flip Classroom video. 3 tips before we start. First, remember you can pause the video anytime to catch up with your notes. Second, you can turn on the captions below so you can watch my words go by on the screen. And lastly, you can play the video at double speed if that helps you get through it faster. Today's topic is a review of our work with sequences and series and the binomial theorem. So first let's take a look at sequences and series, do a few problems, and then we'll dive into the binomial theorem. So first off, we had a bunch of formulas in this chapter, and so I've just repeated them here for you. You should have these in your notes in various places, and also they are in the IB formula booklet for your use on the test. Okay, so arithmetic sequences, we had a formula to find the nth term, and it was just listed this way. D is our common difference. Remember, arithmetic sequences are formed when you add or subtract the same number to get each additional term. So they increase or decrease arithmetically. And so the key there is your common difference. That's what you use to move along the terms of the sequence. So this formula is the first term. You can get the nth term by taking the first term, multiplying the difference by n minus 1, and that would give you the nth term. So you can have some very simple plug-in steps to find like the 7th term or the 28th term, things like that. Now, when we talk about these things as series, that means that they have an end. A sequence goes forever, it can be infinite. A series stops. And then the nice thing about that is that when you have an endpoint, you can add the terms up in the series and get a total for that. So here we had 2 formulas for the sum of an arithmetic series. They're pretty simple. It's n over 2 in both cases. And then this one's more simple. If you know the last term and the first term, you just add those up, multiply it by the number of terms divided by 2, and that gets you the total, the sum of that arithmetic series. Now, this one allows you to do the same thing, but only knowing the first term. If you don't know what the nth term is, all you need to know is the common difference and the number of terms. And you can use this formula to calculate that sum as well. Okay, moving along. Geometric sequences. These ones have a R value. That's this number here, R. That's the common ratio. So instead of adding or subtracting the same number to get successive terms, we multiply by the same number to get the next term. So that number is R, common ratio, and this is our formula for the nth term. It's just the first term times that common ratio to the n minus 1 power. So remember, we're multiplying by our successive times, so that's just R times R times R, n times, or R to the n, or R to the n minus 1 in our formula. Now we have 2 ways to sum a geometric series, and this formula here and this formula there, they're almost identical. They pretty much work in the same situations. I tend to like this one a little bit better. What we have is to get the sum for n terms in a series, we just take the first term, we multiply it by R to the power of the number of terms we're summing up, and then we take 1, we subtract that, and then we divide that by R minus 1. And that would give us the sum of n terms of a series with that first term and that common ratio. Pretty simple. This formula just switches that. So instead of R to the n minus 1, we have 1 minus R to the n, and instead of R minus 1, we have 1 minus R. Now, there may be a few problems where you would prefer to use this version of the formula because of how the math works out, and that's fine. Either one of these will work just fine. Now, an infinite series where the terms keep on growing is considered divergent. Each successive term is bigger and bigger and bigger, and that can be bigger in the positive direction or bigger in the negative direction. That's called divergent. It does not converge towards a number. Now, a series that each successive term is smaller and smaller and smaller is considered convergent because that series is going to grow by less and less and less and less with each term you add. So a convergent infinite series can be summed up. So normally you have to have an n to sum a series. But if that series is convergent, then we can use this formula to find its series without specifying how many terms. And it's a really simple one. It's just take the first term, divide it by 1 minus the common ratio, and that gets you the sum of the infinite series. Okay, so that's the one case where we can actually sum up an infinite series. Now, before we do some examples, let's take a look at the types of tasks that you're going to need to do with arithmetic and geometric sequences and series. So that's just right over here. Here's our tasks. First off, you need to look at a series and be able to say whether it's arithmetic or geometric, because if you can't tell, then you don't know which type of formula to use for that. Second thing, look at it to see whether it's convergent or divergent. That's a good thing to know. If you're asked to sum it up, then it has to be a convergent sequence. Finally, you're going to be asked to find individual terms. We'll give you some information and ask you to find the 8th term or the 6th term or something like that. You're going to need to find sums. We just went over the formulas for those. And then there's tricky problems where they give you some of the information and they ask you to find the common difference or maybe the common ratio or maybe the number of terms. So they might actually give you the sum for, say, a geometric series and ask you to find the 3rd term using this formula. So the interesting thing is that sometimes these get actually kind of challenging because you have to figure out how to use what you know to find out what you're being asked to figure out. Okay, so here's one of those problems that's a little bit less straightforward. We're not just asking you to find the 6th term, giving you the formula or the various information that you might need. So check this one out. We're being told it's an arithmetic series, okay, so we don't have to determine whether it's geometric or arithmetic. We're told that the 15th term is 143. We're then told that the 31st term is 183. And that's really all we're told about this sequence. And now we're being asked to find D, the common difference, and the first term. So what I want you to do, pause the video and see what you can come up with for solving this problem. All right, so I did a first step for you here. We know that the 31st term, which is 183, we're going to take the 15th term and we're going to add some common differences to this term to get to that one, okay? So how many common differences are we going to add? Well, this is the 31st term and that's the 15th. So we're going to subtract 15 from 31 to get how many differences we need to add to 143 to get 183. So now, pause the video and work that math to find D. All right, so here's what I did. I just got my 16 there, so that's 16D, subtracted 143 from both sides, divide through by 16, and I've got my common difference is 2.5. Now, what I want you to do is find U1. Okay, I got you started. 143, there's our 15th term. It's going to equal the first term, that's our unknown right now, times n minus 1 times our common difference. So our n for this one, this is the 15th term, so it's 15 minus 1 times 2.5. So pause the video, finish this up. All right, here's what I get. I moved it down, 14 times 2.5, that gives me 35, subtract from both sides. U1 is 108. All right, one last step on this problem that we're working on. I reproduced our U1 is 108, our common difference is 2.5. That's all we need to talk about this sequence. This prompt, find the smallest number of terms that exceed 1,000, okay? So I want you to start by writing the general term formula for this sequence and then using that to answer that question. Here's what I did. I just set this to 1,000. So if that term, we don't know the n for it, but if that term is 1,000, then I have my formula here and I can solve for my n. So I went ahead and just did my algebra to do that, and I got n equals 357.8. Okay, hopefully you caught the mistake there because I'm not done. So take a look at that and figure out what needs to happen. There is no 357.8th term. We have 357 or 358. So 357 won't be big enough. It will be less than 1,000. So the answer to this is the 358th term. All right, let's do a problem with a geometric sequence. Check this one out. A convergent geometric sequence has a sum at infinity of 120. Okay, so this one is a convergent sequence, so we can get a sum for it, and that's 120. If the common ratio is 0.2, find the sixth term. Okay, so pause the video, think about that for a minute, see if you can work this one out. Here's your way in. The sum at infinity is the first term over 1 minus r. So now you have enough information here to figure out what u1 is, and then once you know u1, you can figure out what u6 is. So see if you can bring that one all the way home. Pause the video and then come back. All right, I just did my plug-in step here. I put my sum at infinity of 120. I did my u1, don't know what that is yet. 1 minus r, my r is 0.02, so I get u1 over 0.8, multiply through, and I get u1 equals 96. So there's my first term of my sequence. Now, to find the sixth term, I have to move over here and use my nth term formula for a geometric sequence. So that's un times equals u1 times r to the n minus 1. Did my plug-in step, u6 is 96, that's my first term, times 0.2 common ratio to the n minus 1, looking for sixth term, so that's 5. Do my work, and u6 is 0.03072. So the sixth term is pretty small. Let's tackle the binomial theorem and the binomial expansion. There's a lot of moving parts in here, but if you want the points, you've got to be able to do these. So let's take a look. Quick review of Pascal's triangle and how that relates to the variables in the binomial theorem. So the triangle is constructed just like so, with each number being the total of the two numbers diagonally above. And you can just build that triangle all the way out. Okay, so the row numbers and n and the power and r, all of those things relate in a very specific way. And there's one thing you have to realize is that the row number starts with n being 0 and the power being 0. So the first row of the triangle relates to an expansion with a 0 power. Now this has its basis in combinatorics, so if you're curious to see how that teases out, you should watch one of the first videos in my series on the binomial expansion. So check this out. So row number 1, n is 0 and the power is 0. Row 2, n is 1 and the power is 1, and so on. So we count up. So what you have to remember is that if I'm looking at the fourth row of Pascal's triangle, I'm looking at an expansion with the power of 3, okay? And the trick for that, I think, is just look at the diagonal one below, the inside diagonal. So this inside diagonal here is the power is 4, so this row here deals with an expansion with the fourth power. So what I want you to do is pause the video and use the triangle here to do this expansion. This will just be a quick little warm-up. Pause the video and do that. Okay, I wrote out the first step and I kept everything in place. I didn't do any gymnastics in my head. I just wrote down everything. So I write my term number from my triangle. Remember, I have the fourth power, so that would be the fifth row. So I write down my 1 for the first term there, and then my x to the 4, because that's my power, and then my 2 to the 0. So remember, the powers count down on the first term and count up on the second term inside the binomial. So this goes from 0 all the way to 4, and this goes from 4 all the way to 0. And you can see I've just done that all the way through. If you're right here right now, pause the video and simplify that step for the expansion. All right, so here's what I get. I just did all of these combining steps here, and I've got my x to the fourth, 8x to the third, 24x squared, 32x plus 16. So that's the expansion, and that's how I use my triangle to get all of my information in the right place to do that. One of the things we learned to do at the very end of our treatment of the binomial theorem and the binomial expansion was we learned to find specific terms in large expansions. So if you had an expansion to the 10th power, that's a lot of figuring out to do the whole expansion. So you could be prompted to find the 6th term in the expansion. So there's basically 2 parts to that. You have to figure out the coefficient from the triangle, and then you have to use that coefficient along with the individual components of the binomial that you're expanding. So let's break that down into the 2 parts. The first part is finding the coefficient from the triangle. And they give us a formula for that. This is the NCR, and it's just n factorial over r factorial times n minus r factorial. And what this is the n is the power on the binomial, and the r is the term number minus 1. So if we want the 10th term, r would be 9, things like that. And we do have a notation for this as well. This can be written as nr. You can do it that way as well, and you've seen that earlier in our chapter. So let's put this to work. Here's our formula. Here's the prompt. Find the coefficient of the 4th term for a plus b to the 6th. So pause the video, use what you've got here and that formula to find Pascal's triangle coefficient. So I just did my plug-in. I figured out my n is 6, my r is the term number minus 1, so my r is 3. I did my plug-in step there. Now, what we like to do with factorials is we like to cancel before we actually calculate. You can just do 6 factorial on your calculator and divide it by 3 factorial times 3 factorial. You can do that. But I think this is a better step. Plus, if you see a non-calculator portion of your test, then you won't have that tool. So I expand out my 6 factorial, 6 times 5 times 4 times 3 factorial. That's what's left. And I can cancel 2 of those 3 factorials. And now I have 6 times 5 times 4 over 3 factorial. I broke my 6 down into 3 times 2, and then I brought my 5 times 4 over, and then my 3 factorial is just 3 times 2 times 1, and I can cancel these 3's and these 2's, and I have 5 times 4 over 1, which is 20. So that is the coefficient from the triangle for an expansion to the 6th power. Okay, so that got us part of what we need. We found this. But to do a problem, we have a second step. We have to take the individual components of the binomial and raise them to powers as well to find the final term. So let's do that. Okay, so let's bring this home and find a full term out of the expansion. So for the nth term of a plus b to the n, here's the full formula for that. Here's the piece that we already did. That's the NCR. That gets us the number out of the triangle. And then we also have to multiply that by the first component of the binomial to the n minus r power, and then the second component of the binomial to the r power. Okay, so what I want you to do is pause the video. See if you can do this one. This one's a pretty straightforward one compared to how complicated the other ones can get. So we want to find the full 5th term of x plus 3 to the 7th power. So pause the video, see what you can do. Let's see how you did. So my NCR calculation uses my n as 7 and my r as 4, not 5. It's the term number minus 1 gives you your r. And so I plug that into my factorial equation and I get 35. So make sure you can do that and get to 35. Then I take my 35 and plug it in here for my formula. So there's a 35. And I'm doing my first component of the binomial, that's the x. So this would be x to the n minus r. So that's 7 minus 4. So it's x to the 3rd. And then it's the second component, which is my 3, raised to the r power, which is 4. And so when I crunch those numbers, I'm going to get 2,835x to the 3rd. So that's a pretty straightforward one of these calculations. So let's move on and do one of the more complicated ones. Okay, so here is a complex problem that basically uses the same process we used before, but there's an extra sort of critical thinking piece to find out what term you're after, because this binomial is a little bit complicated. We have our x term here, and we have an x underneath our fraction right there. Okay, so let's look at the prompt. Here is our expansion, these two components to the 8th power. And it's asking us to find the term in x to the 8th. So you have to unpack that a little bit. It's actually pretty straightforward if you rearrange this prompt. Basically, it's find the term that has x to the 8th power in it. So you're going to have a whole bunch of terms from this expansion, and one of those terms is going to have an x to the 8th power. And that's the term that we're after. So you have to do a little bit of thinking ahead of time to figure out whether that's the 3rd term or the 9th term or the 2nd term, etc. So we've done a couple of these already in class. If you're feeling bold, pause the video right now and see if you can figure out which term we're after. Okay, let's see how you did. This is just sort of like a partial analysis just to get the power on x. So we're not finding individual terms, we're just getting the power on x. So the first term, we're going to have a component from the binomial, from Pascal's triangle out in front of all of these terms, but I'm not worried about that right now. What I want to do is just find my power on x. So the first one is going to give me my x to the 3rd raised to the 8th power. Actually, not that. Just raised to the 8th power because we're marching down from 8. So this one's going to be to the 8th power, and then the second component is going to be to the 0 power. So this is going to give me my first, or a partial calculation for my first term in this expansion. So what I can do is I can just focus on my powers of x. 8, or x to the 3rd to the 8th is x to the 24th, and then x to the negative 0, which is what happens when you put it under the fraction bar. It's not going to do anything, it's still 0. So this one's going to be x to the 24th. So we know it's not the first term. That power is too big. Let's try the second term. So now we're going to have x to the 3 to the 7. We're counting down from there and we're counting up from there. So this is going to be 21, x to the 21st power. And this is going to be minus 2 over x to the 1. You bring that up, it becomes a negative 1. So we subtract. So this is going to have us with x to the 20. Now, we're going down by 4. And you're going to see we go down by 4 each time. And so if you're feeling confident, you could stop there and you could just count down by 4s. But you can see I've done my math here, and I'm indeed going down by 4. I go from 20 to 16, subtract 4 again on my power. I go to 12, subtract 4 again on my power, and I'm at 8. So that takes me from the 1st to the 2nd, 3rd, 4th to the 5th term. So we haven't calculated the rest of that term. There's more to it. But we know that the 5th term is going to have a power of 8 on the x. So now we can come back and use this full formula to figure out what that 5th term actually is. All right, I'm going to want you to do that. I changed the prompt now to find the 5th term because now we can be specific about it. So here's your binomial raised to the 8th power. I want to use this formula to go ahead and find your 5th term. Okay, now that we did all that, this is actually a pretty quick calculation here. I just had to figure out my n is 8, that's the power. My r is 4 because I'm looking for the 5th term. So r is the term number minus 1. And I just did my plug-in with my formula here. So I did my n factorial over r factorial times n minus 4 factorial. I did my first component to the n minus r, which is my 4, and then my second component to the r from there. So I just plugged in my components here into my parentheses. So that's a nice clean plug-in step. I haven't done any math yet, okay? Then I evaluated 8 factorial over 4 factorial times 4 factorial. I get 70 from that. I did a quick peek at my Pascal's triangle, and indeed, the 5th term in that particular row is 70. So I'm like, yes, got that. And then I did my x to the 3rd to the 4th is x to the 12th. I did my minus 2 over x to the 4th. 2 to the 4th gives me 16. X to the 4th gives me x to the 4th. There's an even number of negative numbers raised to a power, so that ends up being positive. It's important that you do that because if this was an odd power, this term would be negative and our answer would be negative. So then I just figured the rest out. I multiplied by 70 by 16, got my 1120. I subtracted my 4th power because it's under the fraction from the 12, and I got my 8th power. And so I've got some nice confirmation here. I wound up with 8 as my exponent, which is good. I should have that because I know that from the previous board. So there you go. I forget how I start that. Does it go,
Here, I can
That's all
hope
for
the video was
today.
helpful. I can
What?
put it.
Now that you've watched the video, write down any questions you still have so you can remember to ask them in class next time we meet. Also note that you can watch the video again if you want to deepen your understanding or patch up any gaps. Finally, give me a like and subscribe if you enjoyed it.
Yeah!